Right, so good day, everyone. You are welcome to today's session. And in today's lesson, we are looking at constraint optimization using the Lagrangian multiplier method. This is often used in economics, right? Now, in the field of economics, we mostly want to optimize functions. Now, in the theory of production, when we move to production, what we know is that firms want to maximize profit, right? They want to maximize profit, and also they want to minimize cost. Yes, in the theory of consumer behavior, you will know that individuals want to maximize utility, right, from the consumption of certain goods. So most of the times, the profit comes in a function. In this case, we can have a profit function, we can have a cost function. Now, with the profit function, you would want to maximize that function. With the cost function, you want to minimize that function. Or with the utility function, we want to maximize. So we can be given any function at all to find the best solution. So in optimizing these functions, we want to find the best solutions to this function. However, in the constraint optimization, we are given a budget constraint. So here there is a budget constraint. We are limited or we are restricted in the quota or the amount of goods we can consume or goods we can produce. So we employ this mathematical tool known as the Lagrangian multiplier method in order to find the optimal solution to a function that has a constraint or a budget constraint. So basically, this is the idea behind constraint optimization using the Lagrangian multiplier method. Now I'll quickly take you through the steps how we are able to apply the Lagrangian multiplier method. Now, what are some of the steps we have to do in order to get an optimal solution? Right. So first, what we have is that you can be given any function, let's say f of x, y. So f is a function in terms of x and y. We can be given a function like that, and the constraint can look like this. Maybe let's say g of x y is equal to k, right? So we are given the objective function. Now we call this the objective function. Then we call this the constraint function or the constraint budget. Now, in forming the Lagrangian, which is represented by this symbol, what we do is that we write our objective function f of xy plus some lambda into bracket k minus j of xy. Don't forget that this is the constraint, right? Oh, sorry about that. So this is the constraint, right? So this is how we form the Lagrangian equation. Then we use this to find the best solutions or the optimal solution to the functions, right? Now, note that lambda here is what we call the Lagrange multiplier. The Lagrange multiplier. Now, it tells us that for any unit increase, right, for any unit increase in the constraint function or in the constraint budget, how much will the objective function change? Now, the Lagrange multiplier, which is lambda, tells us something. Now, this is the interpretation. It measures the change in the optimal function whenever there is a 1 unit change in the constraint or in the budget constraint, right? So by how much will the objective function change whenever the budget constraint changes or there is a 1 unit change in the budget constraint? That is what the multiplier tells us. So now after you form, so this is your first step, after you form your Lagrange multiplier, the second thing is we want to take the partial derivatives. So how do we do that? Now, what we want to do now is that we want to take the partial derivative, that is the so this symbol. Don't forget that this is the Lagrange equation. So we want to take the partial derivative with respect to x, then with respect to y, then we also take it with respect to lambda. Forgive my denotation. Mostly we use L to represent the Lagrange equation. So you take the partial derivative, right? You take the partial derivative with respect to x. So this is how mathematically we write it. This is the partial derivative with respect to x, the partial derivative with respect to y, and then the partial derivative with respect to lambda. Then from these equations, we are going to get a system of some linear equations. Then from there, we will be able to find the value of x, find the value of y, and then the value of lambda, so that we can make some interpretations. So with this idea, we are going to look at one example. We will pick one example and then go through these steps to solve for x and y. Now, in this example, we are told that a firm produces two goods, and the goods are x and y. Now, due to a government quota, so there is some sort of limit on the production of these two goods. So due to a government quota, the firm must produce, subject to the constraint x plus y equals 42. The firm's cost function is given as c into bracket x of y, which is equal to 8x squared minus xy plus 12y squared. So here you can see that we are given a budget constraint. It means that the budget constraint just tells us how many possible allocations of x and y, or the production of x and y, that we have to produce, such that we should meet this limit. When we combine the various combinations of good x and good y, we should produce 42, only 42 units. So there is a constraint here, and we are given the cost function. So this is the firm's cost function, and this is its constraint, or the budget constraint. So we are going to, basically what we are going to do is we're going to find x and y, right? Now we first have to construct the Lagrangian equation. And I told you that the Lagrangian equation is, so basically it is the cost function xy, c of x of y, plus some lambda. Then we bring in the budget constraint, which will be 42 minus x minus y, right? We already know the cost function to be 8x squared minus xy, then plus 12y squared, plus some lambda 42 minus x minus y. Now this becomes our Lagrangian equation. And so it is out of this equation that we are going to find the partial derivatives with respect to x, y, and then lambda. So first, let's find the partial derivative with respect to x. This is the same as delta L over delta x. Don't forget, this is the symbol for the Lagrange. So, and I'm very sure that you know how to find a partial derivative. What it means is that when you take the derivative of this function, this whole function with respect to x, that is what we are doing. And so we are going to get 16x minus y. Of course, in this term, there is no x. So taking the derivative with respect to x will just give us 0. So we don't need to write anything for this. Now, when we come here, we are going to get minus lambda, right? Don't forget that when we expand this bracket, we are going to get 42 lambda minus x lambda minus y lambda. So when we take the derivative with respect to x, we are just going to be left with negative lambda. So you call this equation 1. Then we find a partial derivative with respect to y, which is del L del y. Now we are also going to take the partial derivative of this whole equation with respect to y. This time around, this goes to 0. Of course, there is no y here, so we have 0. But here we are going to get minus x plus 24y. Then here we are going to get minus lambda. So we call this equation 2. If you are finding problem understanding how to take partial derivatives, I have a video on how to find partial derivatives of functions. So you can go and check that video out and then come back to this particular lesson. So now we have the partial derivative with respect to x. We have the partial derivative with respect to y. We want to take the partial derivative with respect to lambda. So this is what we want to find. This is the last one that we want to find with respect to lambda. So let's go back and look at the equation. So of course there's no lambda here, so this is 0, 0, 0. Now when we come here, in fact, when we take the partial derivative of this whole thing with respect to lambda, we are just going to be left with 42 minus x minus y. And I hope you can see that. So here we have 42 minus x minus y. Now you call this equation 3. So we have three set of equations. We have equation 1, we have equation 2, and then we have equation 3. Now out of these equations, we are going to find the value of x and y. That is what we want to do. Now mostly, so let's quickly write the equations again. So for the first equation, we have 16x minus y minus lambda. We have 16x minus y minus lambda to be equal to 0. That's the first equation. For the second equation, we have minus x plus 24y. So negative x plus 24y minus lambda is equal to 0. And the third equation, we have 42 minus x minus y is equal to 0. So this is our equation 1, equation 2, equation 3. I just repeated the same equations. It's the same thing. Now in equation 1 and 2, we want to eliminate lambda. So we want to eliminate lambda in equation 1 and 2. So what we can do is that we can do equation, let's say equation 1 minus equation 2. Doing equation 1 minus 2, so 16x minus negative x will give us 17x. The negative y minus 24y will give us negative 25y. Of course, negative lambda minus negative lambda will just give us 0. So this is equal to 0. Now we can make x the subject here. So 17x is equal to 25y. And hence our x will be 25y over 17. So you can call this equation 4. Now what we want to do is we want to put equation 4. We want to put equation 4 into the third equation, which is this one, this equation. So what we are going to have is we're going to get 42. Wherever we see x, we are going to substitute 25y over 17. So we have negative 25y over 17. Then minus y is equal to 0. The goal here is to find y in this equation. So we can multiply through by 17. Right, so let me come here. Let me divide this page and let's do it here. So now, if you multiply through, you're going to get 17 multiplying 42 minus 25y over 17 multiplying 17 negative y multiplying 17, which is equal to 0. Now 17 times the 42 is going to give us 714. Right, then negative, of course, this will cancel this, so we have negative 25y. Then we have minus 17y is equal to 0. So basically we want to group like terms here. So negative 25y minus 17y should be equal to negative 714. Now what is negative 25y minus 17y? That is 42y. Negative 42y is equal to negative 714. Because we want to find y, we divide here by negative 42, divide here by negative 42, and then we find out that y is equal to 17. So now this is the value of y. Now the next step is to find the value of x. So from equation 4, we can put y equals 17 into this equation where we have x to be equal to 25y. So our y becomes 17 over 17. Of course, clearly this cancels this. So our x is reduced to 25. So now we have x to be 25. We have y to be 17. Let's go ahead to find lambda. In finding lambda, we can substitute the value of x and y into this equation or that equation. Now let's pick the second equation. So in picking the second equation, so let's just do with the first equation so that we can go off with these negatives, right? So in doing that, we're going to have 16x, and don't forget that our x is already 25. Our x is 25. So we just substitute it there. Now what is y? Our y is 17. So negative 17 minus lambda is equal to 0. Of course, here we move lambda to the other side. We are going to get lambda to be equal to, what is 16 times 25? That is 400 minus 17. And the final answer is going to be 300 And so what can we see? Now we can see that x is 25, y is 17, lambda is 383. Let's write that. So x is 25, we have y to be 17, and then our lambda is equal to 383. Now let's check if this is true. Don't forget that the budget constraint was x plus y should be equal to 42. So let's check. Now 25 plus 17, of course, indeed, that is 42. Now what it means is that the firm should produce 25 x good. So 25 number of x good and then 70 number of y good in order to minimize its cost. Now what we can do is that let's substitute the value of x and y into the cost function, right? What was the cost function? The cost function was giving us 8x squared minus xy plus 12y squared. So we have 8x squared minus xy plus 12y squared. So we are going to substitute the value of x and y into this equation to get the cost, the total cost involved. So x is 25, so we have 25 squared minus we have 25 multiplying 17 plus 12, and y squared is 17 squared. So we quickly need to solve this simple equation. Now what is 25 squared? Of course 25 squared will be 625. So we have 8 multiplying 625 minus 25 times 17 plus 12. Now what is 17 squared? Now 17 squared is going to give us 289. So now we break this, we simplify this. 625 times 8 is going to be 5,000 minus what is 25 times 17, we are going to get 425 plus what is 12 times 2, is it 289? Yes, 289. We're going to get 3468. So now we have this. Let's check 17 squared 289. Yes, that's it. So now we have 5,000 minus 425 plus 3,468. Our final answer is going to be 8,043. So what it means is that if we want to, this is the total cost the firm is going to incur if it produces 25 amount of X good and 17 amount of Y good. This is the total cost that the firm will incur. Of course, the critical point X and Y being 25 and 17 are minimum point. And sometimes you can go ahead to check if they are minimum point by doing the what we call using the second derivative test, right? Now we want to use the second derivative test. So we want to find Lxx. This the partial derivative of course, we have already found this. So we are going to differentiate this function again with respect to x. And when we do that, we are going to get 16. Can you see? When we differentiate equation 1 with respect to x, that will give us the second derivative of this function with respect to x. And definitely that is going to be 16. So we will have 16 here. Now when we differentiate this with respect to y again, we have already found this one. So this equation, which is the second equation, if we differentiate it with respect to y, we are going to get 24. And these are positive numbers. These are greater than 0. So of course we can see that the points, the critical point 25 and 17 that we got earlier are actually minimum point. And this is the total cost that the firm will incur if it produces 25 amount of good X and 17 amount of good Y. Now the lambda has an interpretation. As I started earlier, I told you what the lambda means. So now, given that our lambda is 383, we are going to interpret this. Don't forget the interpretation I gave to you. So here what it means is that if we are to increase the production quota or the budget constraint, which is x plus y equals 42. Now if you are to increase this by one additional unit, then the firm's total cost, the firm's total cost will also increase by 383. So that is the interpretation. Now, what it means is that whenever there is one additional unit increase in the production quota or in the budget constraint, the total cost will also increase by this amount, and vice versa. If there is a reduction or a 1 unit additional unit reduction in the budget constraint, the firm's total cost will also reduce by this amount. So that is the interpretation of the lambda. In today's lesson, we have been able to solve the problem and the constraint optimization using the Lagrangian multiplier method. And I believe that now you are expert. Whenever you are given any function together with its constraint or its budget constraint, you should be able to find the value of x, y, and then lambda, and then interpret them appropriately. Thank you for joining to this session. I am glad that you understood everything perfectly. And in the next section, I hope to meet you as well. Make sure that you do like, share, and then subscribe to this channel so that whenever I upload any new lesson, you'll be notified. Thank you.